I'm glad you're here, because I would have kept talking to the ether all day. Been a while since that happened. I was messing around with this a little bit. Firstly, sorry for being so late. Let me restate the important bits of what I was just talking about on mute. I am going to check this, make sure it actually works. And I have brain fog because I ate a very good meal. And now everything in my body wants me to fall asleep, which is one of the reasons that I am doing this so late, ironically. But anyway, so these are just some, like this is way more complicated than you'd think it needs to be, but I have to do level conversion because the pico over here runs at 3.3 volts and does not accept 5 volt inputs. So I have a couple of bus transceivers moderating between the two sides, but basically I've got the address bus and the data bus hooked up, so it's set up to just read, and then I've got the chip select going over here, and I've got this guy is connected on the back of this chip to the reset, so that we can actually reset the goddamn chip. And I just want to do this really quick to do a quick check using the pico whether I can actually read this thing at all, or if the chip is dead. Wareworm said, I rewatched the last day's stream, and if I got it right, then pin 30, 31, 32 all have plus 5 volts, so write and reset signal? Yes, on the this thing, they are all bussed together. And those pins are, what are those going to? Let's revisit. So yeah, on the, I can tell you for sure, on the EEPROM, this actually is VCC, and then this is write enable, which is active low. So that's fine. That should be high. Where are you? Here we go. Yeah, so that's power, then write enable, and then no connect. And then the only place those go is to this chip. They don't go anywhere else. So, yeah. Just FYI. To answer that, I don't know if it was a question, but yeah, 32, 31, and 30 are all 5 volts. They're tied to 5 volts in the cartridge. Yes. So anyway, I guess let me just get this plugged in and start up Thani and see if I can just even read a register and then reset it. Try reading a register again is what I am feeling. As soon as I can get this plugged into the USB port. Plugged in. Cool. Where is Thani? Thani! Wareworm said, I mean, you have 2 extra wires. You're right. That is true. Yeah, as far as having to run the extra header and everything, so. Yeah. Not a bad idea. Okay. This is running on the Raspberry Pi Pico. Cool. So, let me check in case this is an important message on my phone. Okay. I mean, not so important that I need to stop streaming or anything. Okie dokie. So let's set up some pins here. Boy, I wish I was good at Python. From machine import pin. And let me do it this way. Data equals, let me see if I know how to do this. Let me see real what if I do map range 0, I don't know, 10. Is this how this works? And then lambda. I forget the syntax for this. Is it just the name of the argument? And then, I don't know, 10 times x. Boy, I really hate that. Function object isn't iterable. Apparently I don't know how to use range. Oh, or is the lambda first? The lambda is probably first. Map lambda x 10 times x range 0, 10. And then I have to iterate over that, so because that just gives you an iterable thing, doesn't it? So for value in print value. Okay, apparently that's not how that works. Welcome to Learning Python with Joe. Print. Yay, there we go. Okay, that is how you do it. Because this is how I want to make my pins. So let's do data equals, yeah, same thing, map, and our lambda is going to, our range is going to be the pin numbers, yeah. So lambda x, and we're going to do pin x, and then these are all going to be, on the data it's all going to be in, pin dot in. And then we just do range 0 through 7, because I have the data bus hooked up to GPIO 0 through 7. So range 0, actually 8, because it's where you're starting and how many you want. So let's see, data 0. How do I make that into a list? Can I just data equals list data? Data 0. Yeah, there we go. Cool. Okay. So that gave me a really easy way to get a bunch of pins made real fast. Address. Let's do the same thing. So I'm gonna do, because I have two ranges of address. The only addresses that I've hooked, the only address pins that I've hooked up are the 0, 1, and 2 for selecting a register on the doodly-doo on the floppy drive controller, and then I also have 17 and 18 for, you know, the gal. The rest are floating. I don't intend to read from anything except for the floppy drive controller here. So anyway, let's do header low equals map lambda x. We're going to do the same thing. Pin x pin, but these are outputs, and my range is going to start at, how did I do these? Oh boy, how did I set this up? So data 1, 2, 3, 4, 5, 6, 7, 8, and then, yeah, and then it's immediately my address. So 8 and 3. And then address high is going to be basically the same thing. Map lambda x pin dot out. But my range now is going to be 8, 9, 10, 11, and it's just going to be 2. And that is my address 17 and 18. And then finally, reset is just a lone pin. That is on pin. So that's do them in sequence. Chip, or I'll just call it CS, whatever, equals, it's going to be a new pin. It is on 11, 12, 13, and it is also an output. And finally, reset is pin 14, also an output. Okay, so am I also able to, because I should be able to do this too, right? Like I should be able to do fun things like I did map, where my, well, let's do this. For each value, nope, it's just for value in map, lambda, whatever, and this one is going to map over all of the data pins. So if I wanted to print the values of the data pins in a nice, convenient way, we do map lambda x, and we, for x is going to be my pin, and then we just do pin value over the data pins. Print value. There we go. That seems like a thing. So let's try and do this real slow like. Let me make sure things are initialized properly. So CS should be high. I don't want that high. I don't want that asserted yet. Reset should be, we have to look at the data sheet. Wherever that was, here it is. So reset. Oh, now you decide to scroll slightly less chunkily. Nope, it's back to chunky. Okay. A high level on reset places the processor in a known idle state. There you go. So I actually guess let's just go ahead and reset this bad boy. So reset low, reset high, reset low, and now that chip should be in a good state. So theoretically, if I set let's do our mapping stuff again. How do I want to do this? Because I want a nice, easy, fast way of setting all the values in my address pins. Well, whatever. I'll just do it manually real quick. So address low. Oh, right. I actually want to do that same thing. We're going to convert this into an actual enumerated list. So list address low. There we go. Now I can reference these by their actual indexes. So address low. We were trying to access register 4 before, I think so. So let's do address. Whoa, hey now. Address low 0 is 0. Oh wait, that's not how that works. Index out of range. Really? Is that what you think? Did I? Is that not? Did I name it? No, I did. I called it adder low. Let's just run this again. Sure. Adder low. Right. And then adder low equals list. Low, adder low is an empty list for some reason. Okay. Oh, does range not work the way that I think it does? Is it like this? Is it actually 8 and then the place to stop? So 8, 9, 10, 11, 12. Okay, great, cool. low to enumerate it, and adder low. Oh, let's do length again. I just want to be sure, because if I accidentally did 9 data pins, that would be good to know. Yes, okay. Whoops, whoops, whoops. Let's redo a little bit of this. So data equals, let's just list these from the beginning. List map range 0 through 7 inclusive is how it works in Python, apparently. And then address low is going to be list map bloobity 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 bloobity, and this should be 8, 9, 10, 11, so to 11 inclusive, and address high is the same thing. Except it's only 2, and it starts at 12, it starts at 12, and ends at 13 inclusive. And then the rest were correct, I think. Let's see, that would put that would make something not right here, because wait, 8, 9, 10, 11. It's still 4. And what am I on? Let's do address low one more time. What I'm on is delicious hamburgers. 8, 9, 10. Yeah, that's way off. And then address high is going to be 11 and 12. There we go. There we freaking go. And then let's just remake sure reset and CS were set up properly. See, like that's not even right. I'm looking at it. Reset is pin 13. I was way off this whole time. Reset is pin 13. CS is pin. Would that be pin 12? What is going on here? What have I screwed up? I bet. Yeah. You know what I did? I'm glad I caught that. I didn't skip over one of the grounds here. There we go. Okay, now everything lines up. Now everything's starting to make sense. Now the picture is starting to come together. So yes, chip select is in fact pin 13, and reset is in fact pin 14. Nope. Chip select is 13. Reset is 14. There we go. Okay, let's try that same thing again. Let's make sure chip select is in fact high. Let's reset. So reset dot. I'm going to check this with an LED too. So let's do reset low, reset high. And while that is high, let me grab one of these LEDs and check that pin, just to make sure things are actually like getting through. You know, to sanity check my sanity check. So reset is on 32. So firstly, did I connect up voltage properly? Yes. Wait. Yes, but it seemed very dim. Is this 3.3 volts for some reason? Or is it just that my lights are so very bright? Hold up. What is going to my 5-volt rail here? Is anything going to my 5-volt rail? What have I done? What on earth have I done? Bear with momentarily. Oh, okay. That's right. That is wired right. I just think, I'm not sure how I'm getting any voltage out of here, because I don't think my 5 volts is actually connected up to the Raspberry Pi's 5 volts. Anywhere. That's a problem. So I guess I'm going to give myself a wire and fix that. Hey, look, a wire right here. Let's connect V-bus to the 5-volt rail. There we go. Now it should actually light up good. There we go. That lights up like in a sensible brightness. Which means I'm going to have to do this reset thing over again. But at least I don't have to redefine the pins. Let's check over here, see if it's getting through. Did I wire that up correctly? Yes, yes, yes. You can't see that it's behind my fat head. Fat head. 5 volts. Okay. That's good. All right. So let's do reset low, reset high, blah, blah, blah. Chip select should already be what it is. Oh, apparently by doing that I reset this whole thing. Cool. Brilliant. Yeah. At least it has history still. Okay, pins reset up. How about I just take this and copy it somewhere, huh? There we go. For later, in case I lose all of my progress. Okay, so, since this reset, let's make sure CS is high, yet again. Reset, low, reset, high. Ooh. I hope everything's okay up there. Find pin 32. Is, let's see, we start at 27 over here, so. Hello, Trade MC. Good to see you. Okie dokie dokie dokie. So, starts at 27, I need to get 32. 27, 28, 29, 30, 31, 32. That looks high. Oh, I lost it. I hope somebody saw that. Nope, it was behind my fat head. 27, 28, 29, 30, 31, 32. There you go. There you go. And let me see if I can hold that in place with one hand, which is probably a pretty solid no. 27, 28, 30, 31, 32. Oof, oof. Okay, just long enough to reset dot low. Yay! Okay, it's actually connected to the right thing. Neato! Okay, so theoretically, our floppy disk controller is now reset. Let me check what Wireworm's been saying. Trade MC says, or Wireworm had said, power LED for the win. In time. And Trade MC says, ooh, floppy drive time. Sure 'tis. We haven't done much floppy drive anything yet so far, but we're slowly getting there. Okay, let me... And since you're just... What the fuck? Okay, did that reset the Raspberry Pi? Something about me switching windows, that particular key combination is like... Let me do reset again, just to see if all of my stuff is still there, or if I accidentally reset the Raspberry Pi by doing this, because that would be annoying. Reset high again. 27, 28, 29, 30, 31, 32. Oh, well, yeah. It complained that reset isn't defined, so I guess, that's not great. Apparently my hotkey for switching back to this desktop resets the Raspberry Pi. Cool. Okay, we'll just not do that for a second. Please bear with while I redo all of this. Make sure chip select is high. Make sure reset is low. Reset high. Reset low. Okay, back where we were a second ago. Anyway, I'm just going to make sure I can actually interact with this chip with a Raspberry Pi Pico, because it's a chip I got off eBay. So I probably want to double check before I just start plugging it into the NES and going buck wild and really tearing my hair out, wondering why nothing is working when it's because this chip is a dead chip. So let's set some address lines. So like I was doing before, firstly, right, this is actually a list now. Neat. Wait, hold up. Did I still screw this up? Because it says there's only 2 entries. Ooh, that's cool. I didn't know this was a thing. Come on, man. Was I still doing this wrong? Well, okay. Let me do the data pins. Or I guess let me just do. Well, yeah. Let's start with the data pins. Let's just start at the top. 08, and then do len data is 8. Okay, so I was right the first time. It's start and count. Again, welcome to Joe Learns Python. And so, but then that's still confusing here. I guess it's up to, but not including. Maybe that's what it is. And we'll do len address low, which should be 3. Yes, okay. Very good, very good. So we'll do address high 2, and that will be up to, but not including 13. Awesome. All right, cool. So let's just do address low 0. Can I just set it to 0? Well, I'm just going to use low. So that's my, these are literally address 0, 1, and 2. So address low, and I'm trying to select register 4. So 1 is also low, and then address low 2 is high. Then my 17 and 18, I configured that to, I mapped this to those being 0, right? Yes, I did. Address high, 0 low, and address high, 1 low. Okay, so that should be my address setup. So if I enable chip select right now, it should, I can't think of any other thing that I need to set up here. So unless this is wrong, or my understanding of interacting with it is wrong or something, if I dump what's on the data lines right now, well, sorry, if I lower to chip select, which let's just go ahead and do that, and then I dump what's on the data lines, you know what? List, map, the lambda is going to be, I don't know, p for pin, p dot value, yes, and then we are iterating over the data pins. That works. So it's still all 0. That's fun. That's cool. That's fine. Let me just make sure it's actually like not a me problem here. And let's take D0, which I think is over somewhere over here. Let me make sure. D0 is same side as pin 1, pin 13. Pin 1 is over here, and that is 16, 15, 14, 13. And just jam that into 5 volts. And okay, so it is in fact passing stuff through here. So is it the chip not working? Is it me not understanding the way this is supposed to work? Is it... Oh, it could be many, 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 many things. Let me do some simple LED things. Trade MC said, not using list comprehensions? I don't know Python. I don't know Python. Chandra says, do we have Jupyter Notebook for MicroPython? Would have been easier. I don't know Jupyter. Trade MC says, it's got an editor window at the top where I could run from. That is true. Many ways to do many things. Anywho, let's just check some stuff. So, firstly, chip select going into this guide. Firstly, let's make sure power is actually going to the PAL as expected. It is. Okay, so if I look back, oh, you can see that. It is. What am I looking for? Right, I am looking for WinKuppel, and I am looking for... What is my... Okay. So the chip enable is on pin 2, and it should be low right now. And it is. I would love to show you my board, but if I switch screens and switch back, it's going to reset the Pi Pico again, which is super fun. But I will just describe to you what goes on. Firstly, okay. That actually went back. That's good. Okay, let's raise CS. And yes, that is hooked up correctly. I can confirm. I am poking it with an LED. It just went high again. CS.low. Okay. And then what are my other inputs? Just to make sure everything is actually doing what I am thinking I am telling it to. So 3 and 4 are A17 and A18, which should be 0. Let me confirm. Those are both low. And then I guess the final check is my outputs. So ROM chip enable on pin 19 should be high. It is. I promise you. Floppy drive chip enable should also be high right now. Both of them should be high because chip enable is high. Wait. No, chip enable is low. Okay, so chip enable is low. Did I just lower it? Yes, I did. So chip enable is low, but because A17 and A18 are both 0, chip enable for the ROM is high, and chip enable for the floppy controller is in fact low. The write output is high, as we've hard-coded it to, and... Oh, fascinating. Maybe this is where our trouble is coming from. This could be the whole thing. That would be nice. To recap on what I am saying to myself here, the pin 16 floppy read signal is high. Would you look at that? Why would it not be low? It is currently set to FDC chip enable B delay, which is, let's see. So that is coming from, oh, do you think maybe I ran it from the wrong pin? So what should be happening, again, describing what's on the board that you can't see right now. It should be this pin, let's see, pin 18, floppy drive chip enable, which is properly low right now, the way it's supposed to be. Goes to the floppy controller, but also is supposed to be going to pin 5 here, going back into itself and using the PAL as a delay line. So let's see what's on pin 5 really quick, and then it should just be coming out. Basically, the this last line says the read output is just that exact signal. So pin 5. 2, 3, 4, 5. Yeah, I definitely have this wired up to something wrong. That's got to be it. Because I'm looking at it, and I'm poking pin 5, and that's supposed to be hooked up to the floppy drive chip enable, which is low, which is correct. But it's in fact high. So I bet money that I wired that up to... I sure did. I wired it up to the ROM chip enable. Well, did it take setting up a whole Raspberry Pi Pico thing to solve that? Apparently it does for me. Trade Epsy says, does it get an external clock? It does, but it's hooked up. I would switch to it, but I can't. Trey, were you here when I discovered that I can't? I have this OBS screen bound to Control Shift F2, and apparently that also triggers whatever hotkey is the Thani reset the Raspberry Pi Pico command. So I'm just not going to do it for a minute. Okay, cool. It was ridiculous enough that I wanted to make sure that was known, because it's stupid. Oh boy. Right, so I was fixing that thing. Sorry, you can't watch. I know you want to watch. You can't watch. Truly a sad day. Okay, this is going to be fun. This is going to be one of those I need 3 hands type situations. Or I can be clever and use gravity and a pair of tweezers as a third hand. You missed something really cool. I'm sorry. You'll never be able to see it again. Okay, that's actually soldered to the right thing now. And of course, in traditional fashion, I didn't disconnect power or anything, because we go hard here. Okay, let's see. So now, the write signal is high. The read signal is actually low now. Neato, neato, burrito. So let's go back over to Python, and let's just chip select high. Now let's just reset the whole freaking thing, just to be sure. So let's also do, I'm pretty sure reset was already low, but let's just make sure. Reset high, reset low, and now it is reset. Now let us chip select low, enable that, and finally, still all zeros. Very good, very good. Well, at least something. But everything still looks reasonable, I guess. Let me see. Yeah, right is still... Let me check the actual... what the actual values on the pins on the PLCC are. Where is select is the fourth one in from the left. Just making sure that that is actually connected. Okay, I'm poking it. I'm poking it right now. Let's do CS. Hi. Yep, that's getting through. That's connected to the right spot. And CS. Whoa. Cool. And read is active low. Let's make sure that's getting to the right spot. So that is the 1, 2, 3, 4, 5, 6th one inboard. 1, 2, 3, 4, 5, 6. And it looks like it's low right now, which would be what I would expect. Let's do chip select high and chip select low again. Yep. Okay. So the thing is, reading the data sheet, because there's like nothing really else that's going on here that I'd need to care about for the connection to the PC. Unless there's something weird, like there's a max time on the data bus, which I doubt. Usually, pretty much everything, if you, have read enable on the data bus, then it will just put the data on the data bus until the cows come home. What am I even looking for? The chip select, the read, the write, they look like they're hooked up right. Oh, I was going to look at the definition of that register again. Main status register. And just check. Oh, I should double check that the address pins are connected up right too, because that would also be a thing, wouldn't it? Anyway. Main status register, I believe it had like hardware reset states. So I should be seeing. Nope, that's data rate select register. Main status register. Okay, so maybe all zeros is correct, because all it can tell me is that on hardware reset, this will definitely be 0, and these might be anything. Okay, cool. I mean, I could say, let's read from the data register, but that's just gonna... Wait, are there any other read-write registers that I can access? Is the data rate register. That's write only. I can read from the... Oh! Digital input register is basically the decoded current head value, I think. Anyway. So this will probably just also have zeros. These are not accessible to me. Digital output register, read and write. Interesting. What is that one? Because right now I can only read. Unfortunately, I could alter that, I think, but can I? Maybe. But right now, whatever. Digital output register. That was the one I was looking at, right? Digital output register is at 2. Yes, that was the one I was looking at. Digital output register. Do you have any cool default values? No. Also all zeros. Come on. So I guess I have to send you a command or something in order for you to tell me something interesting. Fine. Okay, well, this is here should I need it. My gut instinct is maybe let's just, because I would need to send commands to this to do something. Yeah, well, just for fun while I have it, let's read this. Wait, okay. Data rate select register. Can I read from that one? Why did I not really see that here? Data, no, it's write only. Damn. Okay, well, let's read from this and let's read from this and let's just see what happens. So 101, it's probably all going to be all zeros everywhere, regardless. And it might be working, and this might have been all for naught. So what was that? The data FIFO is 101. So 0 should be high. Oh, let me turn off chip select too. Okay, that should be high. This should be low. This should be high. And I guess just hit chip select and see what we get. All zeros. Totally expected. Okay. Let's do the digital input register and then F it. We'll reconnect this if we need to. Otherwise, we're just going to say, okay. But we were getting basically bus noise on here before. So if I hook this up and that was the issue, and we do a read from the status register and it's all zeros this time, then that's a really good sign. So maybe just that. And then I need to hook up the reset line and jump like that. So doodly 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 do. What am I doing? Oh, right. I guess I just need to set, that was 111 read. Yeah, so I just need to set address low 1 high. Oh, let me deassert CS really quick. Okay, let's try that again. Address low 1 high, now it's 111, CS low, and read all the values off the data pins. Still all zeros. Still not surprised. Doesn't mean anything. I just figured I'd do it while I am here. Great, so that taught us nothing. Nice. Thanks for enjoying me learning nothing. But, well, nah, we didn't learn absolutely nothing. I managed to discern for myself that this was wrong. And I have a little reset pin just floating around here that I can use for nefarious purposes. Woohoo. So I guess let's just plug this in, run the program again, and see if the actual value it prints is at all different now that I have moved that wire over. Because it would be real neat if it was. It's real nice when, like, all of your problems are just solved, and then you don't have to think about the thing that you weren't sure if it was working anymore. Because it's just working, and now you don't have to worry what's wrong with it. Pretty self-explanatory, really. Wareworm says, the power down flag will change when the chip goes into auto power down. Probably. I hadn't read the details on that, but I don't know how long that takes. Let's just rip it. And watch it just straight up not work. Let's do that whole check to see if the cartridge is actually plugged in via checking the 5-volt rail. Turns out that moving that line actually causes this to start messing up the data bus in a way that it wasn't before. That would be fun. Let's turn this to DC voltage, 10-volt range. And on, and yes. Yes, it's doing that weird thing. There we go. It's different. I mean, we haven't reset it. So I'm gonna see if I can reset it, I guess. Let me poke it. Let me poke. I I think and I'm hoping I can literally just attach 5 volts to reset and not like have to put a pull down on this or anything. Maybe it has an internal pull down or something, but the good thing is that's a different value than we had before. And reset. That's the same value we had before. Yay. Yay. Thanks for nothing. Okay, well, that means we can have a fun time playing with the logic analyzer, right? That's positive. Huh. Boy, that sure looks like bus noise, huh? Sure does, doesn't it? Yeah. Especially the way that it's changing all the time. I hate you, Mr. Computer. Well, let's probe some shit. Yeah, Wareroom said, or it's floating reset. That is also totally possible. Oh, was that an application note for that, actually? Because there is this, what I have wired up on the board was, there's like a couple of like example, like reference implementation schematics. And I wonder, because it's not really quite clear about the reset pin, just like on its normal description up at the top, but if I find that like application note thingy and see what it is doing with it, and if it recommends having a resistor on it, well then that would just answer a lot of questions. Here we go. So yes, this is the one I think I was using. Yes, this is the one I was using as my reference. And reset is just tied to reset on the PC bus. Thanks, that's helpful. You know what I can do? That's a super duper duper super hack. Well, if we're gonna do it, let's just do it. That's been my theme of the day. NES cartridge pin out. Cartridge pin out. Let's see where the reset pin is, and assuming the reset goes to the cartridge, it better. It would be weird if it didn't. This doesn't look like an NES cartridge slot. What? That is definitely not it. One second. Let's see what's on NES Dev. NES Dev. I don't know. Cartridge. Cartridge connector? 72 is us, right? I think. Yes, this looks rightish. Anyway, is there a reset pin on here anywhere? Because it would be really funny if there wasn't. There's this reset on CIC. Is that the same thing? I mean, that's the one going between the two CIC chips, but IRQ, ROM select. Wow, is there not a reset on the cartridge port? Is that a fact? Scan. Signal descriptions. Let's see. PPU. CIC. Okay. Not very helpful. Okay, do I have to steal reset from inside the NES? Or we go with my hacky idea and implement a lil register in the gal. Yeah, I'm just gonna do that. It's easier. Implement a little. It's easier than running a reset onto the main board of the NES. Yeah, let's go to WinKuppel. And then once I have done this, we may proceed to logic analysis. But what we can do is we'll just have another output, and I'm actually going to need to add some connections to the gal, because right now it is not in registered mode, and I am about to add a registered output to it. So, yes. Oh shit! If it's gonna be registered, damn it! What am I gonna use for clock? I guess I can use chip enable on the falling edge of chip enable. Of course, this clock is on the positive edge. Well, it doesn't really matter. Just if that pin changes and the address was let's see. So 15, we're going to call this FDC reset, and we are going to make FDC reset become, when it is clocked, and let's just make a note that pin 1 is going to be clock, but I'm just going to use chip enable for that, and we'll see how that goes. So, this equals if A17 and I don't know, maybe A17 and not A18. Oh boy, this gets back into mapper shit. Because or MMC shit. Because if I want to, basically I just want, if I write to this memory address or this section of the EEPROM banks, I just want to toggle that pin is what I want to do here, which is going to require screwing with the MMC3 again. Well, isn't that fiddly. Well, anyway, we've got our ROM. We've got our ROM at 0. No, we've got our ROM at 1, 1. We've got our floppy controller at 0. So I don't know. Let's put this at 1, and then we'll figure out. We'll just do it. We'll just figure out how to make that happen. A17 and A18 and wait. Sorry, no. Not A17 and A18. So if that is true, then it should be not FDC reset, and in all other cases, so it should just toggle. Let's make sure these are balanced. Open, open, open. Close, open. Open. Close, close. They are totally not balanced. The frick. Open, open, open. Close. Close. Open. Close, close. No, they are totally balanced. You are going insane. So that, or if not A17 and A18. I know the parentheses are insane. I know. Don't tell me about it. And then in that case, it just doesn't toggle. Maybe we do want to run one of the data pins in here somewhere, because we don't know what its initial value is, right? Yeah, shit. We could do FDC reset is if you write to... No, let's just run a data pin in here. We will connect that in a second. So, no, inputs. We are adding an input. So, pin 6, I'm going to make D0. And this will be basically all the same logic. Whoops. Let's just bring that back so I don't have to type it all over again. Or I can just press random buttons and break my computer, apparently. Whoops. Never mind. So let's just rewrite it, I guess. If not a 17... No. If not... Yeah. Not a 17 and a 18. If that is the case... Just sequester those a little bit. Then it takes on whatever is currently on D0. Open, 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 close, 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 whoops. Or, if they are... It doesn't do Control-Z, which is very annoying. It says it does Control-Z. What the hell? What is your definition of undo here, buddy? Okay, let's type this up one more freaking time. If not a 17 and a 18, then use the value from D0. Open, 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 close, close, close. I did the same thing again. Whoopsie daisy. Put an extra guy up here. Okay. Or, in the case of the opposite of that, if not a 17 and a 18. Oh boy, here comes the water softener. Hope it's not too loud. Sorry, it is what it is. This is the way this night is going. Okay, so if not all of that, wrap it again, because I'm insane. I know. Open, open. Close, close. No. Open, open, open. Open, open. Close. Close, close, close. And this won't be D0, it will be whatever the current value of FEC reset is. Cool. Yeah. So, I might have to invert chip enable to use it as the clock here. We'll just see. But this should make this, after I wire up D0 and wire up, I'll just bridge, right now I guess I'll just bridge chip enable and the clock input, and then connect D0 to pin 6. Hopefully, I will be able to flip a pin on and off on that thing. Maybe. Yes? Okay, let's do a twofer right here, because we're gonna need to test that bit of things. So, let's just ignore all this stuff, ignore the floppy drive controller stuff, period, and just in this loop, once we've done get key and once we've done print character, oh boy, now we have to think about the MMC3 stuff. MMC3. MMC3. Okay, so I can use this one, or I can use this one. What controls that? So what controls that is this, and I always write the same thing to it, which is 0 to all of these high bits. And let's see. When I write 0, 8009 FFF is the one that is swappable. I see. This swaps that. So it's going to have to be 8000. And I guess I'm going to need to... I'm going to want to watch that toggle, so let's... how do I want to do this? Let's load a 0, push a with my overuse of the stack, heck yeah. Then after we wait for a key and then print a character, pull a, and then just pull a set stuff. PLA. PLA. Yes, it sets 0 and negative. So we pull it, and then we can just check branch if equal. If it was 0 to a thing where it will toggle it on, toggle reg on. Otherwise, we will. Is there a store X and store Y command? I know there's a load. There is for 0 page, and there is for 0 page indexed, and there is for absolute. Cool. So I'm just going to store Y, or I guess load Y. If the register was 0. Oh, I can just XOR this, can't I? Wait, I doubt there is a XOR instruction. Oh no, there is. Exclusive OR. Well, what do you know about that? So I can just... I don't even have to do this. I will just pull a exclusive OR it with literal 01, and that'll toggle it, right? Am I understanding that correctly? So that should be easy to figure out. So if it was 0, 0 exclusive OR with 1 is 1. And then on the opposite thing, yeah. 1 exclusive OR with 1 is 0. Yes, it will toggle it. Awesome. So then we can just store A to 8000, which will theoretically be our little register, and that should cause us... Oh, also push A to make sure it goes back on the stack so that we can do this and then get the value back again. Very nice. But now we have to do more setting up of the MMC3 so that, what did I even do? I mapped it to 0, 1. 0, 1. So mapping the other MMC3 thing for the floppy drive controller was relatively easy because it just had to be at 0. All zeros. But this one, I have to really think about it. I think... So it's 8 kilobyte blocks, right? Which I determined earlier is 13... That is 13 bits of address. So then we have 19... The mask ROM has 19 total bits of address on it. So I think... No, I shouldn't just assume. Because I'm not quite sure, and I don't, like, it doesn't... I'm not sure if it really says in the MMC3 documentation, like, what the granularity of the, like, value that you write to the bank select register is. So I'm going to need to double check that. But for starters, let's do load A. We need to write it to the register that is for the 8009 FFF area. Also, there's still this weirdness, which I don't get. This is a mappable area, and yet it's also where the registers for the MMC are. I don't quite understand. But theoretically, I can write to anywhere in that mapped area, and it doesn't really matter. Only those high bits matter. So let's not write to 8000, because that's what this is doing. Let's actually write to, let's see, so the registers are up to 8000, which makes sense. Oh, no, so that's the whole freaking thing. The hell? Okay, so, damn it. I think I need to set that one bit for, yeah, this one. I need to set the second to last bit here to 1. Yeah, because I still don't get this. How are you supposed to use this at all? The MMC3 registers aren't there. I don't get it. So, anyway, let's just use this one. Well, or alternatively, let's see. So this is C1000 to D FFF, fixed to second to last bank. How big are the banks? Are they 8 kilobytes? Are all the banks? Is it 8 kilobyte chunks? It's really not clear. Program banks. Right, that's all about our swapping stuff. Blah-de-blah-de-blah. R6 and R7 will ignore the top 2 bits, as the MMC3 has only 6 program ROM address lines. Okay. Okay. I think that tells me that right there. So these must be my A17 and A18. Hopefully, right? 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 Because that's just what the MMC3 supports. But does the MMC3 support chips bigger than the one in Super Mario Bros. 3 with extra address lines? Oh, wait. What? R0 and R1 ignore the bottom bit. Wait. Which ones are R0 and R1? R0 and R1 are character ROM thingies. Okay, so don't worry about those. R6 and R7. R6 and R... Okay. Well, fine. So, how big are the frickin' program ROM banks? How big are they? I'm going to check chat to see if anybody said, how frickin' big are they? Wareroom said, or use an RC net and have power on reset only. That's also not a terrible idea. I hate analog electronics, though. Or use the CE with the address and no register and do a dummy read and have the new CE go to reset. Don't quite follow, but... Trey, I have a... you said, do I have an oscilloscope? I have a logic analyzer, so we will be using that momentarily after I spend way too long working on this piece of crap. I just want to know the bank size, the bank size, the bank size. This is all IRQ stuff. IRQ stuff. Scan through again. So if this is fixed to the second to last bank by default, it still doesn't tell me anything. Well, let's think about this really quick. Here's one way to think about this. So if it says that for data, only these lines are actually available on the MC3. And if the banks are, if we assume that the banks are 8K, that means 13 lines of address for the like non-banked portion. 13 lines to address any given 8K area. And then 13, 14, 15, 16, 17, 18, 19. I'm going to make an educated guess there. I think it's what I have to do. Based on that and the fact that we have 19 address pins available on our map ROM, I think the banks are 8K and these are A17 and A18. I think that's the assumption I have to make here. So I'm just going to go for that. Which would also mean that that second to the last bank thing would mean... What would that mean? Not much for me, because it would... There would be more ones here than just... Yeah, no. Doesn't work for me. So... Let's set... Not only... Let's set this bit so that we're using the bank C1000. So... And then I have to make sure I'm not changing the MMC3 after this and doing that again, because it seems like every time you write that, you can... It alters that flag value, so best be careful. But I think this is the last time that I touch the MMC3. We'll find out real fast. Okay. So, what is wrong with my fingers on this day? Load a literal, so it's going to be, I want this, yeah. So I want this register, that is register 6. So it's going to be hex 06, but then I also want to set this bit, which is going to be bit, and it's going to be 4, so this should be 46. And then I'm going to store it in 8000. And that should mean that this selectable bank that I'm about to set will be accessible from the window at C1000. Cool. And then load a not 00, but in fact, based on my assumptions that I just assumed here, it's going to be... Okay, looking back at this, where did I map this? 01. So it's going to be 00, 01. So it's just going to be 10, 10. And then store that at 8001. And I think that's our mapper setup. Let me make a comment on that. Map MMC3. MMC3 C00 bank 2 mask ROM or 2, I don't know. 2, let's just call this FDC reset register memory area. Sure. And then that means I need to change this code to just write to to C1000. And there's our code. Okay, so let's burn this. Well, let's make sure this builds. And somehow I deleted the part where I pushed this back on the stack. I'm glad I caught that. Oh, also there should be a label somewhere. 212. Why does that make me nervous? Here, let's just build it real quick and run it in the emulator. I was fat fingering a lot of stuff there, and hopefully I didn't do something weird on that line. That would be no fun. Okay, good. Good. This does the right thing, more or less. It didn't blow up in any kind of weird way, so I'm okay with that. And let me go back here and make sure my changes to the gal were actually compiled. Yes, they are. Okay. Apparently, I'm going to do the EEPROM first, because that's what's up right now. Offset to that. Let's actually change to the desk again, since we can do that now, since I'm not using the Pi anymore. Move this over, put it in the thingy. Program banks are 2K in size. Are they? Oh, are they? Are they? Well, we're about to find out if you're right. Oh, no, you say, but then you said Hex 2000, which is not the same thing as 2K. Hex 2000 is 8K, isn't it? Yeah, it is. Hex 2000 is an 8K chunk. But if I wire this all up and we don't see that pin toggle on and off as I type keys into the NES, then we will know that you were... Oh, you were correcting yourself. Oh, okay, sorry. No, we're all on the same page. It's all good. It's all good, my dude. Okay, now to do the gal. Did they make... Well, no, that was a stupid question. I was going to say, do they make ZIF sockets? Do they make ZIF sockets for pins and narrow width packages like this? But, duh. I'm literally about to put it into a ZIF socket. This guy. They let him own a soldering iron. Okie dokie. So that is the... Oh boy. Oh, you know what? I need to switch this to ATF 16B8 B. Now it will filter for me. Haha, yes, there we go. And program it. Yay, okay, that's the software and programmable logic side of things. I don't know if I want to say done. They have had something done to them. Okay, now let's turn the soldering iron back on, because it is cold. And do I dare... Let's move this again. Do I dare disconnect this from the cable? Oh boy. Okay, what needed to go to what? So this is... Let's start with the... Hey, this is now in registered mode sort of things, and make sure output enable is grounded. And a reminder to myself, like I said, I'm just going to connect chip enable directly to the to the clock pin. But if things don't immediately seem to work, the first thing I will try is inverting that whole situation. Good enough. This one is tiny. You think I can do it? Because I never had any doubt. There we are. Okay, that is the output enable pin. Grounded. I think. Okay, that's that. Now, chip select to clock, which we will make this a conspicuously long wire, since it might need to be changed. We'll see how late I can go. The fun thing is, of course, I only have so much time, but I also have work in the morning. So, let's see, maybe I go to 12:30 EST. Right now it's 11:45. And then the rest of the week, you know, there won't be as much time during the weekdays. Because it is what it is. Have I flown too close to the sun? Heck yeah, I've flown too close to the sun. That's not even a question. Okay, and... oh, right, I need to connect up D0. Where does D0 come from? It comes from, let's see, this is pin 1 side. Okay, I don't need to run more wires off here. Let's run it off the EEPROM. And pin... yes, wait, no. Yes, sorry. Going crazy. D0 should be right here. Are you getting a good view of the back of my head? Just want to make sure that you can see that really good. Okay, that seems connection related. Run that on over to... what pin was that on? That is on pin 6. 1, 2, 3, 4, 5, 6. Well, you know what? That is the one unused pin here. Wow. Who'd have thunk it? And it came disconnected. Whoops. I need more solder on that pin. Okay, is that everything? Got my output enable set up. I've got my clock hooked up to. Let's put some more solder on that one. But I've got my clock hooked up to chip enable. I've got D0 going to pin 6, and I will not connect the actual reset thing up yet. I just want to see if this code toggles that register or not. Let's see if it even starts up. Whoop! Okay. Sure does. Typing works. Let's strap an LED to this bad guy. Well, this is done. Okay, so it's what was that? How was that? The output is on pin 15. That is 20, 19, 18, 17, 16, 15. Okay, it's on right now. I don't know if that's right, but it's on. Well, that sure as shooting ain't toggling. Let's go ahead and do that inversion thing and hope I didn't just break this by doing what I just did. But at least things aren't horribly broken yet. So I am just going to, since I'm already over here, what we will do is we will take, well, disconnect this from this. And it could just be because I didn't have the MMC3 stuff figured out just right, but could also be because well, it could be a lot of things. But it could just be because I really need a positive clock pulse here. Okay, so I'm going to feed, no, wrong. That needs to go into input, sorry. So I'm going to pin 7 here. And then I will just use that to invert that signal. And that will come out pin 14. Go into the clock itself. On the keyboard I didn't need to invert the clock. On this I might need to invert the clock. That would be funny. I just blew on the tip of my soldering iron. That's normal. Okay, did I fuck that up? Yes, I did. Damn it. Damn it. I connected to pin 15, which is the register output, not the inverter output. Oh, do. Whatever will I do with this useless melon of mine? Pin 14. Back to clock. Strip? Oh, it actually did. Yay, thank you. Okay. Now, let's do some reprogramming yet again. Back over here. Let's, okay. So pin 6 was D0, and now we're making pin... I'm really dumb. We didn't need to run that into another pin. You know, it's a fact, we're already running chip enable into a pin. I mean, not that that really hurts anything, but unnecessary. This is the thing about a pal, or a gal. Is you can route things internally. You can route them many ways. Okay, I just removed that little thing. So, yeah, we just need to pull from chip enable B. And what we're going to do is we're going to do pin 14 is called, let's just call it chip enable as opposed to chip enable B. Let's do these in the combinatorial entries. Chip enable equals not chip enable active low. Save. Run. Compile. Save it. Yes. Didn't I just save it? That makes me feel weird. Where are the tweezies? Where are the tweezies? Ah, hiding them. Did I load it? I don't think I loaded it. Oh, slow down, bud. Last written, 11:55. That seems good. That seems right. Now you may program. You're not even looking at my screen. Well, it's programmed now. Okay. That's the thing. And you know what I'll do, just to save myself some sanity, is let's just temporarily solder this LED up to the output of this single register deal. Doesn't want to solder, that's fascinating. man. Do it for me. This is becoming a problem. All kinds of quickly. Okay. I think I didn't fuck those rounds up too bad. Do we just hit go now? I think we just hit go now. And then we read chat a little bit. Still not doing anything. Cool. Alright, well that leads me to... It's going to be 30 minutes of logic analyzer time. Everybody's favorite time. And I think first I'm just going to logic analyze this reset thing. See if I'm actually, you know, like sending data to it and stuff. See if the clock is actually clocking. All that good stuff. All kinds of good stuff. Well, let's check chat for a second. Wereworm says, I have seen narrow ziffs. Oh. Oh, Wereworm pasted in a link to Amazon link to narrow ziff sockets, and it just turned it into text. Damn. Santiago said, hello, just stopped playing with an FPGA that I found on a trashed prototype PCB, quite old. I was able to get a UART going on. Kinda hate FPGAs, but this one worked a treat. Go Lattice. You know what? Trash picked stuff is heckin' fun. How's the interface going, says Santiago. You've seen. Santiago says, hey, thanks. I think I'd be cool to do something high speed with it, but I'm not sure what. Was thinking of running like a 6502 or some core there, but way too lazy for that. You know what? Do what makes you happy. And I'm going to do some logic analyzing. It's what the people want. It's what the people demand. Yeah, let's start. Let's just start here and... Because it could be that the MMC3 stuff is not right. So let me probe A17, A18 on there, the clock pin, and the data pin. That should be all I need, right? And then we'll just set a trigger for if clock goes high and A17 and A18 are 0, 1. Wait. Do I have an endianness problem here? Oh, I do. I keep saying 0, 1. It's not. A18 is higher than A17. It's 1, 0. Okay, let's try this really quick. Let's update the software. And change the mapping here to... Oh, no, I did do 1, 0. That's disappointing. That is disappointing. Wait. No. 1. This isn't binary. Oh, 12:01 a.m.? Yeah, it's 12:01 a.m. That's not binary. That's the format for this thingy. So it was actually going to be... It's these two pins, was my understanding, so it's actually going to be 2 zeros. It's going to be 0, 0, 1, 0, then all zeros. Yeah. Okay. Okay, that would be totally wrong. That would have been totally wrong. Let's build it. Let's write it. Let's see if that makes a difference. And then maybe someday we'll get back to the floppy controller. Someday. 29 EE010. Select it up, and here we go. Load up the ROM. It's not the JED, it is a thing called basic.bin. Okay, everything's cool. Let's set the offset like a fool. Okay, let's program. First I gotta put the chip in there, man. But I got a ZIF socket, making everything the shit. Just pop it out and in, and then we can begin with the program. Oh. I do this every time, and pretty good that this is the first time I've forgotten to clear the check ID thingy. Yay! Programmed. Let's watch that make 0 difference. Yes, it still makes 0 difference. That's okay. That's okay. That's all right. Now, maybe it'd work if I hadn't inverted that clock, but I really am itching to stick this logic analyzer on something. So let's do that. Let's put the chip clip on here just so I can get around. And for no other reason, let's turn this off. Oh, come on. You can do it. That seems connected enough. Let's put ground on ground. And then we need, what did I say we need? I'm gonna do, let's go with the clock pin. Okay, so clock is on channel 0. And then, next I need are A17 and A18, which I believe, no, I have no idea what those are. It's clock, then chip enable, then A17 and A18. A17, okay, reminder to self, A17 is on 1. And then A18. Okay, reminder to self, A18 is on 2. And then I want my data pin. Oh, where are my clippies? There's a clippy. 3. And which pin was D0 supposedly on? That is supposedly on pin 6, which was A17, A18, then the floppy drive chip enable delay thing, and then D0. Supposedly. Okay, that is an instrumented thingy. Where is it? There is it. The horrible view of my logic analyzer. So let's do some configuring. And let me know if me flipping over here makes thoughts. I want to edit the format. I want to... Okay, so what did I say? This was clock. done, and that is on 0. And then this is a 17, and that is on pin 1, and then a 18, and that was on channel 2, and then D0, and that was on channel 3. And now let us set up our trigger. So my trigger will be that I want clock to be high. I want a 17 to be low and a 18 to be high, right? And I don't care about D0. And that's that. So let's turn this on and hit run. Derek says HP 1663C, how fancy. You know, lab surplus from eBay. Can't complain. Okay, and yep, that sure isn't triggering shit. So, question is, what up with that? Is it because of the MMC3? Is that what's up? I mean, we captured A17 going a couple times, and let's actually add A18, which has always been high. Is that a probing issue? Why would A18 be high at all? A18 should always be low. Right? Am I crazy? If it's running shit off of... Sorry. If it's running shit off of the EEPROM is mapped at 0, 0, I think. Unless it's mapped at 1, 1. Let me double check. The EEPROM is mapped at something. The EEPROM is mapped at a thing that I did and then forgot. The EEPROM is mapped at... Okay, no. It was the 8000 bank that was mapped to 0, 0. So 0, 0 is our... 0, 0 was the... was the floppy drive controller. And the ROM, the EEPROM. Oh, it's always fixed at 8000. That's right, and it's always fixed at the last. Okay, yeah. Right, it's always fixed at the very last thing, so they would both be on. So that makes sense, I think. Oh, though, you know what? I mean, looking at this right here. So that should be, that should be like A17 low, A18 high. Isn't that what we're looking for? A17 low, A18 high. Yeah. So does that just not line up with clock? Let's see if we get clock 0. Let's see if that situation ever happens. Okay. I mean, it totally does. Am I right into it twice for some reason? Well, let's also look at... Wait, actually, it shouldn't be doing that at all. It shouldn't be doing that at all. I'm not pressing buttons. Shouldn't be doing Unless my, I am assuming. I am assuming like a ding dong. I was pretty sure my get key routine is supposed to halt until we get a key press, but I never actually tested that. Maybe that's the idiocy that I'm dealing with right now. You know how I can solve that? You know how I can do that? Firstly, let me just add the D0 bit here just to see what was being passed in here and if that makes sense. Okay, interestingly, D0 was low every time this happened. Oh, we don't actually have a clock here. That's that might just be weirdness of the 6502. So A17, we actually never have a positive clock edge, so that could also be the issue here. But this is consistent if I keep running it over and over again. So heck it, let's I don't know that it would happen anyway. Let's see. I mean, it is weird knowing that D0 is never... Oh, wait, no. Wait. This is just randomness. Oh, come on. Ah. I want to catch one where D0 is actually high. Huh. You'd think D0 should be toggling. I'm probably not even looking at what I want to be looking at here. Also, these are really short. This can't be right. Our period is 4 nanoseconds. And that is as fast as the thing can go. And that is pretty fast. What is 4 nanoseconds in terms of cycle time? That's very fast. Maybe let's actually bump up our sample period just a touch, because that could just be, we could be looking at a bunch of spurious crap. Okay, let's do 50 microseconds? No, that's way too high, because 1 microsecond would be the inverse of a megahertz. Let's try this. Looks exactly the same, which is weird because I changed the sample time. Oh, but I didn't change my. Oh. But this is. That's my sample time. That's not my actual per division. So it's 1 microsecond per division. Yeah, okay, so that actually makes sense. That actually looks right. Okay, anyway, the other thing I wanted to look at is, like, D0 always appears to be 0, and we don't actually have a clock there. This is probably not toggling, but I'm curious to see on the output if the output is actually toggling. What pin was this? It is 15, 20, 19, 18, 17, 16, 15. Okay, let's run this again and see. No, it is actually always high. At least that's a nice confirmation of that. Sure. I don't know. Let's just try let's just try not inverting the clock / chip select thing real quick. See if that makes any improvement. Sometimes even Logic Analyzer 2 can lead you astray. Okay, so disconnect from here. Reconnect to here. I mean, I suppose I may have to run the CPU clock over here anyway, so I could just attach the CPU clock to clock. But I mean, chip select should actually be derived from that as well, so Alright, we have switched the clock input to being driven by chip select again. See if there's a difference. See if there's any polypicking difference. All right, 0 was clock. 1 was a 17, right? I think. Two was a 18, almost surely. It's gotta be. And number 3, green meanie here, was on pin 6. 1, 2, 3, 4, 5, 6, and that was data bus bit 0. All right. Still nothing on the output. Now it's never getting triggered. That's cool. Switch to clock high, I guess. Whoop, whoop, whoop. Run. 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 Okay, so if this is to be believed, like here is a chip enable / clock, whatever, going, sorry about the hand. Sorry about the hand. Okay, just wanted to zoom in a big touch. Okay, so yeah, it's that chip select happens just a titch before here. That's fun. Still don't know if this is actually like correct, but that edge is happening just a touch before A17 is actually going well. assuming that this is what I think it is, and this thing is just constantly every few instructions writing to our little register deal. Well, this was a... Speaking of no wild goose chases, I'm also just looking at the data line for, it's always low whenever A17 drops, which is, alright. I mean, maybe I'm not grabbing the right pin, but then on top of everything else, it's still not, you know, actually toggling the output. Oi, 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 oi. Oi, oi, oi. Okay, hold up. Here's my last insane thought. I still don't get why this would be doing quite what it is. Why it's making 2 accesses to A17. I don't know. Also, I'm clearly not using, like, read or write. Oh, is it? I don't know. 6502 does some weird stuff like that sometimes. Like, it might just have a cycle that asserts A17 but isn't, like, trying to update memory or anything, and then there's a subsequent cycle that's the actual write. Could be what that is. I've seen that before. But yeah, anyway. What if I just used A17 itself as the clock? Is that insane? It's probably insane. I'm losing my mind. All this just to reset the stupid floppy controller. And bloody, 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 blah. You know what? With the precious time that I have left here, God bless you if anyone is still watching this at this point. Wareroom says 27 hours awake. I feel the urge to pilot heavy machinery now. You were supposed to take a nap in the middle of the day. You were supposed to do this. Derek says, somehow, despite being fortunate enough to have a lot of newish test equipment, my only real logic analyzer is a 1630G. I swear it uses the same font as the Apple II or something very close. Nice. Nice. Okay, so, anyway, that's a wild goose chase. We can figure out a way to reset this later. I mean, we definitely have to reset it, but you know what? We're going to logic analyze stuff. If we are going to logic analyze some stuff, if we're going to logic analyze anything, we should just do the logic analysis on the floppy drive controller, reading blah-de-blah, and see if it's even trying to assert anything on the bus. So, I guess... how shall I do this? I'll do it in timing mode. I will trigger it based on the floppy drive controller chip select signal going low. And we will just look at if the data bus goes low at that time or what. So let's hook up the whole frickin' data bus, and see what it does. Because if we look at it and when chip enable happens there, the bus is not, you know, whatever it is, like A0 or 50. It's 50. I think it's 50. After we assert chip select on the floppy drive controller, then we know it's a timing issue, and the floppy drive controller is at least trying. So I'm going to connect up 0 through 8, or well, 0 through 7 to the data bus. Yeah, yep, yeah. Wareworm says, maybe the RCNet will get you over this dead point. Totally, something like that. Something like that. He said, just do power on reset and solve the rest later. You're right. You were always right. Okay, how did this go? Oh, well, okay, I was also definitely probing the wrong thing, and I had the wrong thing hooked up, but that doesn't explain things because still this should have been getting 0 clocked into it. I am just now realizing that I definitely connected D3 up to SD0 this thing, so whoopsie daisy there. Whoa. Boy can't count. 3, 4, 5. That would make sense. Ugh, looked like I was going to grab 7. I think it is probably getting your time to go to bed. But I don't wanna. I don't wanna. And 7. Okay, that's all the data pins. And I think all I want is just data and floppy disk chip enable, which is doodly 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 doo pin 18. $20, $19, $18. Okay, back to the logic analyzer. And let us reconvert things a little more again. Sometimes I just say words, and they're not, they hold no meaning. We're going to modify this. We are going to rename it date. We are going to 7 through 0. Cool, very good. This is going to be FDC, FDC, CED. Good. And that is going to be on input 8. Let me just double check that that is true. It is true. And set up our trigger. And $X $. That's a new one on me. But we want it, we don't care about data. Oh, is that indicating hex? No, no, it's not indicating hex. Okay, so that can be anything. And it's when the floppy drive chip enable goes low. And it's off, so it will sample every time. But let's, this is going to be interesting. If I just hit run now and then reset it, haha! And I want to switch this to data whole bus. Yay! Zoom in a touch. Zoom in a touch. Let's go back to where it was actually accessing the floppy drive. Put it in the middle of the screen because that's the only way you can zoom on this dumb thing. Okay, so when FDC chip enable went low, there was in fact a 0 on the bus. Which I would have to imagine is not being driven by the floppy controller. I would have to imagine. But it never changes in here, which is fun. Let me add really quick also. Let's attach. But it, you know, I don't know. I feel like this indicates that the floppy drive controller is not putting anything on the bus at any time here. So that's good. I am going to connect up also the FDC read line so you can see what the hell that's doing. And that is on 16. So this is 18, 17, 16. And start this back up again and reset the NES and let's just do that one more time. Oh, and I should probably add that to the format. Modify label, let's call this FDC, or let's just call it read B. And that is input 9. Done. Add it to the output. Did you sample it already? Well, it looks like it has the shifty behavior that we were kind of expecting. Ish. Let's super tighten up our acquisition control. Sample period. Drop it all the way down. So we just want to look at one tiny window. And I also want to alter the trigger. Let's up this to, actually 8 nanoseconds is it, or no, let's change it to microseconds of some sort. 200 nanoseconds? 56 nanoseconds. Just so we don't get anything spurious. Ooh, also, you know what I actually can use? Acquisition control. Let's put this in. Okay, so we see that old A0, and I think I'm basically getting way less delay than I was thinking there. That's probably my issue. Well, I mean, that's probably an issue. So if we zoom in, zoom in, zoom in, scroll, 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 scroll. So we are looking at 5 nanoseconds per division, and I mean our capture period is 4 nanoseconds. So this is read B trails the chip enable by 4 nanoseconds ish. And I think the minimum on that was 5, wasn't it? I mean, that's probably not our issue. It's probably not our issue. Probably. 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 Jacob says, full QWERTY pad, nice. Yep, and it's a pain in the ass to use. It is a pain in the ass to use that thing. There's actually a PS2 keyboard and mouse hookup on the back that I should really just keep plugged in all the time, but whatever. Blah, 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 blah. Blah, 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 blah. Okay, I am going to do one more thing before I just pack it in for the night and just bring, because this is fine. I can bring the NES TV typewriter to VCF. That's fine. And that maybe is what I have to do, because I really should work on some other things this week and set aside time for working on work that pays me money. So I think I do have to admit this ain't happening, which nobody is surprised by. Trade Dempsey says, I'm gonna go to bed, y'all. Nice work. Sure. No, I appreciate it though. I mean, not sure on you going to bed. Please go to bed. Enjoy. Rest up. As far as this being nice work, okay. You're very kind. Yeah, so anyway, last thing I'm going to do is let's just see if we can't get another, well, let me check the data sheet first to make sure that I am remembering correctly that 5 nanoseconds was the minimum delay between chip enable and asserting the read line. Because if it's any more than 8 nanoseconds ish, or let's even just say like 6, giving myself some margin, I am not willing to add more than one extra delay stage here, but I am willing to add an extra delay stage and see if that makes any difference, which it probably doesn't. Where did we find this? Is this searchable? It is totally searchable. What was that? TCE? Nope. Well, timings are usually at the end. Let's look at the end. AC characteristics, bunch of stuff. Write data timing. DMA cycles, host write cycles, host read cycles. Yeah, so that time was from CS change to read going low times 7 was minimum T7. Minimum 5 nanoseconds. Alright. I'm going to try. Also, how wide is that read pulse? I mean, it's, because it says minimum 90. Certainly it's more than 90. Certainly. Yeah, let's see. Seconds per division is 200 here. So this almost fills up 2 divisions. So that is well over 90. But yeah, let's make that trail it slightly more. Let me make one more delay stage. And I'm sure that won't make a difference. I am sure that will not make any difference whatsoever. But I'm going to do it. And I mean, on top of everything else, this isn't reset, so... yeah. About that. This is probably just like a wasted afternoon, but Trey said, "No, that's cool. Enjoyed watching." I really appreciate it. Giving me that morale boost. Yeah, so let's just where is this coming in? So we had a bunch of weird stuff, but mainly on our output side, we had the chip enable for the ROM, we had the chip enable for the floppy controller, one end of which is going to the floppy controller, the other end of which is going into here, and is going out to the read input. So let's steal that and move that down to pin, I don't don't know, 13 or whatever this is. And let's run another wire from that delayed output back through to another input. Where is my strippers? Where is my strippers? They're probably in here. Boo-da-doo-da-doo, coming out of here, boo-boo-boo-boo-boo, going over there, going here and there, going everywhere. Maybe that's my problem. They shouldn't just be going everywhere. And let's make sure that's actually an unused pin. 1, 2, 3, 4, 5, 6 was my last used pin, so yes, I can use this. Can I use this? A little more solder on the thingy. I will say though, this is 100% my experience with this kind of project. Is you bang your head against it, and you bang your head against it, and you bang your head against it for hours one day, and then the next day you come in and you're like, oh wait, and then like you figure it out. That's how it goes. Okay, so I previously had the read signal to the floppy disk controller coming out of the delayed output, but now I have the delayed output going into input 7. And then I have the read signal coming out of, I think that is, oh, let's just count, 20, 19, 18, 17, 16, 15, 14. Let's make sure I wasn't using 14 for anything. 14 was my inverted chip enable. But I'm not going to use that anymore, so. Alright, so let's change this up. It's a me, a bunny hole, says Jacob. My favorite character. So let's call this, well, pin 14 actually is going to be FDC, FDC, RDB, yes, and this we're going to call FDC CEB DEL2. Right, so now this is coming out and it's going into this guy, which is going to be, let's also, I'm going to relabel this D2 just so I can remember that that was connected wrong, but it is still connected, so. And then pin 7 we're calling, well, hold up now. I mean, this is terrible naming, but I guess we're gonna, I will call this FDC CEB DEL3, even because the issue is that these are, since they're just connected by a wire, they're really like the same node. The fact that they have two different names is kind of odd. Maybe I can call this Del2 out and Del2 in. And then we don't have the chip enable signal anymore, but we do have something. So FDC, so this is going to be FDC CEB DEL2 in. Will then be going out FDC RDB, which is what's on pin 14. And is there actually anything else I need to do? I guess I need to do, yeah, that would be important. FDC CEB delay to out equals FDC CEB delay, yes. So the floppy disk chip enable, how does this even go? So the floppy disk chip enable, or no, right? So, right, that's it. So, because we're using the read signal is just the chip enable signal delayed. So, chip enable comes in. I'm just making sure that I can keep this straight in my head. Chip enable comes in, and it is set by these things. And then it also connects to FDC CEB delay, which gets fed out via FDC CEB delay 2 out, which then is connected to FDC CEB delay 2 in, which then finally comes out of FDC read. It's a thing. But let's go ahead and compile it. And whoa. It's complaining about something about D0. Oh. Because this needs to be changed to D2. This is not Vim. Save, run, compile. One warning about missing stuff in the header. Cool. And switch this back to ATF 16V8 and load the JED file that was compiled at 1249. Yes, it was. Good. And prepare for programmation. Just making sure the NES is. Not that I think I will screw things up too bad by yanking chips out of a live circuit, but you know. It's gauche. Yay, it programmed. All right, cross your fingers because this is the last thing for the day. And I guess really all I'm seeing is if the delay is now a little longer, a little more significant, and if it actually makes any difference on whether the floppy drive controller asserts crap onto the bus or not. And I will move forward with this over the course of the rest of the week, but I think I will bring the Raspberry Pi Pico thing back in and modify it slightly so that I can actually read or write, so that I can actually, you know, write things into the registers and make sure that they update things. Yeah, that would be a good idea. So I guess let's slap the harness of stuff back on here. And this goes. And then all of our little wires, like go all kinds of places. They just go all over the darn place. So I think 8 was... Oh, no, I have to wait for it. 8 was the floppy drive chip enable, which is now all the way over on... Where did I put that? Or wait, no. Floppy drive chip enable has always been and will always be at pin 18. Doodly-doo, doodly-doo-doo. This is 8 to good. 20, 19, 18. And 9 is the floppy drive read signal, which is now on pin 14. So that's 18, 17, 16, 15, 14. There we go. And we turn this on, and it takes a poop. A temporary poop only. Okay, and we move over to the thingy-majigger over here. I'm not even gonna, I don't even do words anymore, man. It's just the thingy-doodad majigger. The trigger should still be set up right? Yeah? Yeah, so run. And reset. Hey, that's different stuff. And that is reflected on the screen. But is that actually from the goddamn floppy drive controller? It's hard to say. Let's capture it a few times and see if it stays a little stable. Uh-huh. Nope. It sure doesn't. This is garbage from all over the place, boy. But of course, I haven't reset the floppy drive controller, so let's tap that wire just for fun. Let's tap that reset wire, and then no more. No more. Give me a wire so I can poke some stuff. You know I gotta poke some stuff. I'm feeling rough. I'm calling on wires, yeah. Okay, I think this is 5 volts, and let's just doot it slightly. Doot, doot, doot. Which I'm sure isn't good enough, but I just wanted to do that. Just let me have this. I mean, it is interesting that, like, the bus changes, but it changes sometimes, but is it just because, you know, the bus is floating all over the place and changing its values and whatnot? Probably. Yeah. And we still never really solved at the top of this whether, you know, this floppy drive controller chip works. So anyway, that's that. This is another one of those wah-wah episodes, which, you know, after almost 3 hours, I hope you had fun watching me go wah-wah, because it is what it is. But not the first time, won't be the last time, but it definitely is time to admit that we're not going to have a floppy drive at VCF. Oh well. I mean, that's surprising no one. That was a pretty big ask, but we're going to have keyboard. We're going to have type on screen. It's good enough for me. So I'll get this thing buttoned back up, and I mean, we'll keep I can keep futzing with this all day, and it really doesn't affect. We still have type, and we still have character. And we will get this happening. It's just going to be pain in the dick. So, I think in the ensuing week, we'll keep it light. I will strap the Raspberry Pi up here and just try and drive it directly again, and just make sure the friggin' thing works, and try and understand how to operate it properly. Because clearly there's issues there. And yeah, that's that. So thanks, guys. Jacob says the atom wasn't cracked in a day. Ain't that a fact? Yeah, you don't need to give me attaboys. I know good days and bad days, but I appreciate it. I'm on a stream and I'm sitting here looking at my phone like a jackass. If I want to look at my phone, I should end the stream. Thank you, guys. Good times. I'll see you again tomorrow at 5-ish, as we do. But until then, I guess I'll turn off the logic analyzer. I guess I will go to Facecam and say goodbye. Thanks for tuning in. Still fun every time, regardless. And that, I should say formally too, that's the end of Mega Stream Weekend. I don't intend to do that again. I intend to keep a nice, slow pace with this moving forward. And then we'll see if I film anything about VCF or anything, but it's a good time. I'm looking forward to it. And this week is going to be a nice short week because I'm taking Friday off, and today is already a holiday. It's already Monday. So that's nice. Anyway, I need sleep. Thank you, everyone who joined in for Mega Stream Holiday Weekend. It was actually a bunch of fun. I appreciate you guys for coming. I appreciate more my wife for having the patience of letting me, dedicate the majority of an entire weekend to not seeing her, which is a bummer. So I'm going to do some more of that because I sure do like being around her, and my baby too, as well. I guess that child I have, pretty good. All right, that's that. I'm gonna stop. I just gotta stop making words, except for these words. They're coming. See ya. I'll love.